Previously, we looked at the components of the aircraft simulation. Here we're going to focus on the 6th degree of freedom dynamics under a flat Earth assumption. This is the beginning of our simulation development. Our goals are to explain the 6th degree of freedom equations and then begin construction of an aircraft simulation in Python. This series is going to build the simulation piece by piece, coding along the way. And in doing so, we're going to leave some loose ends at the end of lessons, kind of like unfinished edges of a jigsaw puzzle. But ultimately, we're going to have enough of the picture to actually run the simulation and then continue to build upon it. All that in time. Let's begin our journey with reference frames and coordinate systems. To get to the flat Earth approximation, let's start with the oblate spheroid Earth. It spins about its axis at a rate we'll call omega e. The equatorial plane divides the Earth into two hemispheres. The Earth's center of mass is very near the equatorial plane. We'll assume it's on it. Consider an inertial frame of reference that is fixed with respect to the stars. It does not rotate with the Earth. In this frame, we assign a coordinate system termed the Earth-centered inertial, or ECI, with its origin at the Earth's center of mass and its x-axis aligned with a celestial event like an equinox. It is denoted with the subscript I. Consider another frame of reference in the assumed rigid Earth. Attached to this frame is a coordinate system at the Earth's center of mass that rotates with the Earth. It is called an Earth-centered, Earth-fixed coordinate system, denoted with the subscript E. Let's introduce another coordinate system with its z-axis normal to the spheroid surface pointed down. Its other axes are aligned in the north and east directions. It's in a plane tangent to the Earth's surface. This is the northeast down coordinate system, denoted with the subscript N. The northeast down coordinate system is local in the sense that it travels with the aircraft. Its origin can be assigned to the aircraft body or to the surface of the Earth as shown here. Note, NED rotates with respect to the Earth and the aircraft as the aircraft travels over the surface of the oblate Earth. The aircraft is also a frame of reference. It has a body fixed coordinate system with the origin about the aircraft's center of mass and the x-axis aligned out the aircraft nose. Toward the flat Earth assumption, we'll focus locally around the NED coordinate system. Recall, the northeast directions are in a plane tangent to the Earth's surface. If we view the situation along a slice aligned with the north direction, then we see a line representing the tangent flat Earth plane and the spheroid surface. Here, position is with respect to the Earth's center of mass. Now, assume the Earth does not rotate. This makes the Earth an inertial frame, denoted E. Also assume that the Earth's radius is infinite. Then, our stage for simulation is the flat plane extending from the tangent point, the flat Earth approximation. Therefore, we fix the NED coordinate system to the tangent point T and use NED to quantify aircraft position in the northeast down directions from the position at T. In contrast to the oblate Earth simulation, NED is now fixed to the flat Earth surface. Here, the aircraft angular and translational dynamics are with respect to the flat Earth inertial frame of reference. The body fixed coordinate system and the northeast down coordinate system are the two primary systems used in the flat Earth equations of motion. Now let's define variable nomenclature. Let's take, for example, the aircraft position vector. We have the position variable r. The subscript cm/t means the aircraft center of mass with respect to the point T. What about the superscript n on the right-hand side? It means the position vector is resolved in the NED coordinate system. What about aircraft velocity? Of course, v is the velocity vector. What is cm/e? Right, the aircraft center of mass with respect to the inertial frame of reference in the flat Earth, e. And how are we resolving the aircraft velocity vector? That vector contains three numerical values resolved in the body fixed coordinate system, b. When we take the derivative of a vector, the result depends on the derivative's frame of reference. Here's the acceleration of the aircraft center of mass with respect to the inertial frame, resolved in the body coordinate system. The derivative is taken with respect to the body frame. So the variable gets another superscript, b, now on the left-hand side. This is a little cumbersome. So we're going to omit the left superscript going forward in this lesson. And note that state derivatives are in the body frame for the flat Earth 6 DOF equations. What about angular rates for the aircraft? This variable is denoted omega. How is it expressed? It's the angular velocity of the body frame with respect to the inertial frame. And in which coordinate system do we resolve this vector? It's the body coordinate system. As shown, the angular velocity of the aircraft is out the nose, indicating only rolling of the airframe. Okay, we have coordinate systems, reference frames, and the nomenclature. Let's get to the 6th degree of freedom equations of motion. We're not going to go through their derivation here. Rather, the intent is to present the equations with enough detail to use them correctly in simulation. If you have particular interest in learning more about aircraft modeling and simulation, I'm going to have some recommendations for you at the end of the lesson. The flat Earth 6 DOF equations consist of the translational equations and the rotational equations. These are vector equations, each representing 3 scalar equations for a total of 6 degrees of freedom. The translational equations are derived from conservation of linear momentum. The translational equations say that the aircraft acceleration is due to external forces such as aerodynamic and thrust forces, gravity, and the rotation of the velocity vector. Each term of the translational equations is resolved in the body coordinate system. We see the velocity of the center of mass with respect to the Earth frame. This is the state of the equations. M is mass, F is aerodynamic and thrust forces, as represented by the A and T subscripts. Gravity is resolved in the northeast down coordinate system. But the gravity term is resolved in the body coordinate system through the direction cosine matrix C. Finally, omega is the angular velocity of the body frame with respect to the Earth or the inertial frame. You'll recognize the translational and angular velocity vectors from our nomenclature discussion. The state vector v has velocity components in the u, v, and w body coordinate directions. The angular velocity components p, q, and r are the roll, pitch, and yaw rates, respectively. Gravity is assumed to act normal to the Earth's surface, and therefore is parallel to the down direction in NED. And the external force vector is resolved into XYZ components in the body coordinate system. To compute the gravity term, we'll need to compute the direction cosine matrix, or DCM, that transforms a vector in the northeast down coordinate system to one in the body fixed coordinate system. This is accomplished with a 3x3 DCM. Its elements involve 3 rotations from the northeast down coordinate system into the body coordinate system. These are the roll, pitch, and yaw angles, or phi, theta, psi, also referred to as the Euler angles. We recall gravity acts in the positive down direction in NED only. To resolve gravity in the body frame, we simply perform the matrix vector multiplication. This results in 3 short terms requiring only roll and pitch angle. After computing the cross product on the right-hand side, we can write out the 3 translational equations resolved in the x, y, and z body axis. And this is our final result for the translational equations that we're going to program into our flat Earth equations of motion. On to the rotational equations. The rotational equations are derived from conservation of angular momentum. The resulting vector equation has the angular acceleration on the left-hand side. The first term on the right-hand side is angular acceleration due to external moments. The second term is angular acceleration due to rotation of the angular momentum vector. We'll already recognize some of the variables in the rotational equations. Angular velocity is the state, J is the inertia matrix, M is the moment vector, subscripts A and T denoting aerodynamic thrust sources, V is the velocity of the aircraft. The moment vector is resolved about the roll, pitch, and yaw axis of the body. It says L, M, and N. Angular velocity is P, Q, and R as before, and translational velocity is U, V, and W as before. The last item to discuss is the inertial matrix J. Along its diagonal are moments of inertia expressing resistance to changing the speed of rotation due to aircraft mass distribution. The moments of inertia act about the X, Y, and Z body axes. The larger the value, the greater the resistance. The off diagonal contains products of inertia. These capture how a body rotating in one axis will induce rotation in another due to the uneven distribution of mass. For example, assuming fuel is equally distributed, this aircraft is symmetric about the XZ plane. When the inertia matrix is calculated, then, it turns out that due to this symmetry, the YZ and XY products of inertia cancel, so that they become 0 elements in that inertia matrix due to the XZ symmetry. This allows us to simplify the rotational equations so that when we expand the right-hand side with the cross product and matrix vector multiplication, we obtain the roll, pitch, and yaw equations. Note the double indices XX, YY, ZZ, they've been replaced with X, Y, and Z for brevity. And so we have gone through the 6 DOF equations, starting with their vector form, identifying each term, each variable, and then expanding them to obtain 6 scalar equations that will be core to our aircraft simulation. Some of the assumptions worth noting behind these equations are the Earth is an inertial frame of reference. Gravity is always acting normal to the tangential plane, down and constant. The aircraft mass is actually assumed constant. Otherwise, we'd have time derivatives of J, the inertia matrix, in the rotational equations. The aircraft rigid body is assumed to be rigid, so we're neglecting structural modes. To code the 6 DOF equations of motion, we need to establish a convention for naming variables in the code. Of course, the coded variable name needs to be consistent with the variables in the equations. But also in the variable name, I'd like to have the coordinate system as well as the units. The units are helpful to avoid conversion errors and variable ambiguity. For example, here's the vector velocity and its components. We give the first element, the x-axis velocity, a name, where we have the variable, followed by b for body coordinate system, followed by its units, MPS for meters per second. The y and z axis velocities easily follow. What about the y-axis moment of inertia? Its name, its coordinate system, and its units. Can you tell what this variable is? It's the yaw rate along the z-axis in the body coordinate system with units of radians per second. With those preliminaries aside, let's take a look at the code. The canvas is blank. What's our first piece? Well, we're going to need a main folder to hold everything. Inside, we'll have our driver, a conductor of our orchestra. Call it main program. And just a reminder, we're doing this in Python. For now, the driver will do three main things. It receives data from the user, it runs the simulation, and it plots the results. In that middle step, running the simulation, we're going to call two things. The governing equations, here we'll call that script flat earth EOM, and a numerical integration method, also located in its own folder. For now, that's just forward Euler. We'll start with the focus of this lesson, the governing equations. I'm in Visual Studio Code. On the left-hand side is the File Explorer showing the file structure and driver main program. In governing equations, we see flat earth EOM, which is shown in the editor. For those new to Python, I'll have some recommended resources in the video description. In viewing this code, our objectives are to 1. View how the 6 DOF can be coded in Python, and 2. Check for errors in coding the 6 DOF equations. We can't run the code at this time. Our primary verification is going to be visual inspection. And note that this code is for educational purposes. It's not optimized for speed or brevity. Let's begin. Up top, we import the math and NumPy libraries. We define the function flat earth EOM for now with just a few input arguments. These arguments are time in seconds, the instantaneous state vector x, and a dictionary of aircraft model data. The function returns the left-hand side of the equations of motion. On line 40, we pre-allocate the left-hand side of the equations. The derivative dx dt is here called dx. Next, we assign the current state values to variable names. The first 6 variables are 6 DOF states. We also have placeholders for the roll, pitch, Euler angles, so we can compute gravity in the translational equations in the body axis. Below the states, we assign mass and inertial data from the AMOD dictionary, or aircraft model dictionary, to variables. We have a spot for air data calculations and a spot for an atmospheric model, both coming soon. Gravity in the northeast down coordinate system is normal to the tangent plane. Therefore, only the z component is defined at this time. Applying the DCM with theta and phi, we resolve gravity in the body coordinate system. In the future, we'll have force and moment buildups from aerodynamic and thrust data. In the roll and yaw rate equations, there's a denominator with inertial terms in it. We'll define that denominator on line 86, just before we get to the translational and rotational 6 DOF equations. Here is the roll axis or x-axis velocity equation. Is it coded correctly? To help answer this, I'm going to say some things that may seem obvious, but they're important questions and comments because they may reveal potential sources of error. First, how is the flat earth EOM function used in the context of this simulation? What I'm getting at is it's used for numerical integration purposes, and as such, we would like the instantaneous time derivatives of all the state variables. That's the left-hand side of the equation. We compute the left-hand side by evaluating the instantaneous right-hand side. So all the variables on the right-hand side have to be instantaneous values or constants. Knowing that the input argument x is the instantaneous state and the variables on the right-hand side are assigned their values from x or are constants, then we can conclude this equation computes the instantaneous time derivative of the state x. And this will hold for all subsequent equations. Next, is the index of dx on line 90 consistent with the equation on the right-hand side? Well, index 0 corresponds to the x-axis velocity. And comparing the code to the x-axis velocity equation, we see there's consistency. Essentially, we can conclude the left-hand side matches the right-hand side. Finally, is the equation coded correctly? There are several checks. First, are there the same number of terms? We have 1, 2, 3, 4 terms. Yes. Second, are the operations between the terms correct? Plus, minus, etc. Yes. Third, are the operations in each term correct? First term, 1 over m times fx, check. Second term, gx, check. Third term, w times q, check. Fourth term, v times r, check. Now, the variable names match the intended variables. Mass in kilograms, check. Body x-axis force in kilograms meter per second squared, check. Body axis gravity in meters per second squared, check. Body z-axis velocity in meters per second, check. Pitch rate in body coordinate system radians per second, check. Body y-axis velocity in meters per second, check. Yaw rate in body coordinate system radians per second, check. Finally, are the units correct? That is, do the units of each variable make each term have the same units as dx on the left-hand side? Yes. That's a laborious process, but it will help find errors if you're trying to track them down. Now, we can go through the remaining scalar 6 DOF equations. I'll just show you the equation, and you can pause the video and go through the questions if you like. Comment below if you find an error. The y-axis velocity state equation. The z-axis velocity state equation. The roll state equation. The pitch state equation. The yaw state equation. We have placeholders for the kinematic and position equations coming soon in future lessons. We've just gone through the 6 DOF equations coded in Python. Let's move on to numerical integration methods. Inside the script, it's very simple, just the forward Euler method. Let's go on to the main program driver that brings the previous 2 scripts together. First, there's the initialization. This includes the initial conditions, for now just empty variables, the assignment of the initial conditions into an array, the initial time, duration of simulation, and time step size. Now, we simulate, or numerically approximate solutions to the governing equations. For this, the time vector is constructed. The initial condition is assigned to the solution array, and the time vector, the solution array, and the time step size are input to the forward Euler integrator. The integrator works with the governing equations to return the fully populated solution array if all goes correctly. Finally, the solution array data can be post-processed as needed or as preferred for plots and other visualizations. This brings us to the final stage, plotting results. In future lessons, we'll expand this section to observe the data. In summary, we've gone through the anatomy of the 6 DOF equations of motion that are core to flight simulation. We've also looked at these equations in Python and reviewed how they could be orchestrated with a main program script like a driver and a numerical integrator. I've provided you the introduction to get started. Now it's your turn. Study these equations yourself, start your own simulation in Python or whatever language you prefer. If you're serious about learning more to develop 6 DOF simulations and aircraft simulations in general, I recommend becoming more familiar with the derivation of the equations in this series, and you can do that with Stevens & Lewis's second edition, Aircraft Control and Simulation. That's our primary reference for this series. The first chapter, about the first 50 pages, has everything you need to create flat Earth and oblate simulations, apart from the aircraft model definitions. Now there's a third edition to Stevens & Lewis. It's got the same material in the first chapter with some updates to how it's presented and reordering of information. I'd also like to mention Modeling and Simulation of Aerospace Vehicle Dynamics by Peter Zipfel. I've got the first edition. It's a wonderful book. It's written in order of increasing complexity, starting with 3 degrees of freedom, then 5, then 6 degrees of freedom simulations. The nomenclature you'll find is really different from what we have in this series, but nonetheless is an excellent reference. I'd like to thank each of my Patreon subscribers. You make this content possible. You make Learn GNC possible. Thank you very much. Until next time, good luck. Access this lesson and more at learngnc.com.